What I'll start with is yesterday, Himani, I think she had asked that question whether the solution spaces would contain the or solution space is part of the null space. These two are two different things. I thought of adding it on the visualization. So what I have done here is, if you see this particular place, we have a place to, let's say, for example, we can enable x is equals to b, which is non-homogeneous condition, and x is equals to, or let's say, homogeneous condition, right? So once I enable x is equals to b, now there are two different things that you would want, that you would see. Let's say, for example, I have, let me remove the null space and also the column space. Okay, now you are able to see the solution space, which is in purple color. But you could also see that the solution space is not passing through origin, right? This is origin. This is actually a part of it, which is called as particular solution. This is XP, right? And yesterday I told you about the general solution is particular solution plus the null space solution. So if you add null space to it, sorry, this is null space basis, but if you add null space to it, these two are the different spaces that you see. The teak blue color is the null space, the purple color is what the particular solution one, right? So where the particular solution lies, let's say, for example, this is the particular solution, but this entire space that you see in purple color, this is the solution space for you, which contains the particular solution plus the null space. Now, if you add teak blue color plus XP, which is the null space plus XP, you eventually get the solution space. That's what you're looking at. Okay. So the answer to your question, Himani, if you're already here, the solution space actually does not contain the null space. So it is different by an offset, and offset depends on what is the value of your particular solution. Because if you see x is equals to xp plus null space, right? This xp is what gives you the offset. Good.
This X spacer is the anchor point.
This is the anchor point. That's
And purple you are saying is solution space.
the purple is the solution space. The anchor point is a part of solution space. And what you have here is the deep blue color is the deep blue color is the null space. Okay. This is the null space that you see. The greenish, bluish greenish shade, whatever that color is, I don't know. But this particular color is the null space, and the solution space is the purple one. Now, if you think of why solution space is not passing through origin, and null spaces would definitely pass through origin. If you see, this actually passes through origin, but solution space is divided by an offset. So if you could think of any equation that you would have, which is non-homogeneous, it would be of this form: 2x plus 3y is equals to 10, right? And because it is not 2x plus 3, these equations would pass through origin. These equations will never pass through origin, right? And that's why you'll always see the solution space not going through the origin at all, because you have a biased oh, sorry, you have something which gives you the offset. In this particular case, when you write general solution is equals to particular solution plus the null space solution, in that case you are saying that general solution, whatever the space the general solution lies, it should contain the particular solution and should also contain the null space, right? Because this is what tells you ax is equals to 0. Now the null space is what you looked at on that diagram, or sorry, on that HTML as the teal blue space, and this is what the null space was. And then you had added the solution, sorry, the particular solution to it. Now there are various different things that you could.
Sir, where all the solution are lies, that are the
Can you share this HTML as well?
Yeah, definitely. Go ahead. Who someone was asking that question.
yeah. I'm asking like what is the solution space where all the solution lies? That space is a solution space.
Yes, exactly. The solution space is where all the solution lies.
Okay, thank you.
Now, yesterday we also discussed about two different views. One is row space and column space. Now, for this matrix, if you think about all rows, 1, 2, 3, 2, 4, 6, 1, 2, 3, they are all dependent on each other, right? They all are dependent. Whether you look at from row perspective or you look at from column perspective, all the rows are interdependent on each other. So there is only one unique information from the column perspective. There is only one unique information from row perspective. So the rank of the matrix is always going to be one, right? Now, because let's say, for example, because there is only one specific special information that this matrix is giving you, so the row space would be a single line. That's what you see here. The row space is this yellow line, right? This is the row space for you. Now the column space, same would be a single line. So those two are the row spaces and column spaces. Good.
Yes, sir.
Sir, if we
Okay.
combine row spaces and column spaces, will we get the full span?
No. That is not the idea. Row space is a different meaning altogether. Row space is, think of, yesterday I told you, think of each row as a different user. Row space tells you what is the property. Is there any space which defines all of my user which exist on my platform? Let's say you have an application, a mobile app, and you have millions of users on that mobile app. And if you would want to know if there is a space which can explain all the users that I have on the platform, the row space just tells that. Column space, on contrary, is, let's say you are evaluating those users based on certain things. How many number of time they open the app, how many number of time they click on ad, how many number of time they watch something, right? So if these dimensions that you are measuring against are there unique dimensions, or let's say, for example, are there spaces that can combine all the dimension and then picturize you that space is called as column space. Column space is the dimension space, the feature space, you can call it as. The column space is the feature space, where all the features in machine learning, whatever model that you're building, let's say you build the models on certain features, right? The column space is the feature space that you have.
Okay, sir. So from the Netflix example that we saw yesterday, we can say that row spaces are the user spaces or the data point spaces, and the column
Right,
spaces are the feature spaces.
right,
We
that's
can
right.
include that.
Yes,
Okay,
yes, yes, definitely.
now I got it. Thank you.
Okay. Okay.
Sir, can you please apply a rank nullity theorem on this example that you're showing?
Yeah. So think of it as rank is one, okay, right? Nullity is two, and that's why you see the null space being, now let me show you the null space. The null space being shown in this bluish color as a
Hmm.
plane, right? So 1 plus 2 is 3. There are three dimensions. 1 plus 2 is equals to 3,
Yeah.
right?
So null space
Good.
is two dimension.
Yeah, that's what you see. The null space is a
Yeah.
plane.
Yeah.
Now this is true for even for homogeneous equation. You see in the null space is two-dimensional.
Okay. Yes. Okay.
Good.
Sir, sir, is there any left null space? Some of the readout I found left null space.
Yeah.
What is that,
There
sir?
is I'll tell you about it. Yeah, we will go through lecture 5 and then I'll tell you. I'll tell you after decomposition. You will understand that. Okay.
Okay, sir.
Okay.
Thank you.
Sir,
Okay.
if I may summarize all these things, so we are doing in order to miss, like, as per the ML requirement, if any clustering we want, or how close we are to the solution. So for all those cases, these things would be applied. If I
Yes.
may.
Let's say, for example, if you would want to find out, think of each unique row here. If you would want to find out how much dimension, let's say there could be millions of users right? Let's say each row, there could be millions of rows on your application. So there could be millions of users. Now, are actually millions of users give you the question that you should be asking is these millions of users, do they give me million dimensions or these millions of users uh, stay in much lesser dimension, maybe in 3 dimension or 4 dimension? There could be millions of users, but they could all be coexisting in smaller dimension, right? Or let's say in 3 dimension or 2 dimension or 5 dimension, whatever it is. These millions of users might not be all different. You're able to understand that, right? So because let's say, for example, in this particular case, there are 3 users, but all of these 3 users that you see in each row, they all are similar. They all are same, and that's why the row space is a single line. They all of those users, they all on this particular yellow line, right? There are 3 rows, but 3 rows eventually give you the space which is one single line. That's what it means. Now, once you have that conclusion, you would be able to do geometry. And this particular lecture, you will understand what do I mean by geometry. You'll be able to find out how similar, how close two different vectors are, which are on the same space. Now think of any 2 vectors which are on the steel plane. Okay. If there are 2 vectors, I should be able to find out how similar they are, right? Now we know that they are on the same dimensions. They are on the same plane. We should be able to find out whether they are similar or not, how much, if they are dissimilar, how much dissimilar they are, what is their length, and so on. So these are the things, these are the questions that we are going to answer today. And then you will find out, once you know similarity, you can cluster something which are similar. Then you can distinguish something which are dissimilar. Those intuitions would be built based on today's lecture. Good. Should we start?
Sir, sorry, sir,
Sir,
one last
one
question,
last
sir.
question.
Yeah.
The image HTML, I see nullity is 2 and rank is 1, right? Sir, how can
Right.
we distinguish nullity as two units? Because I see only one plane, right?
Right.
The color, whatever
This
is being
particular
shown.
example, yeah, this particular example has, I mean, I could have what I could have done is I could have used a different example wherein there are 2 unique informations. In that case, rank would have been 2. Now, if rank is 2, then the null space would have been 1. Let's say there are 3 dimensions only, because we can only visualize 3 dimensions with the no, so we only can visualize 3 dimensions right now. We know
Okay.
that, right? So I have just shown you that, let's say we stick to 3 dimensions. Now, the only thing that we need, that we can play with, is either rank would be 1 dimension, nullity would be 2 dimension, or rank would be 2 dimension, nullity would be 1 dimension. That's what I can visualize. I cannot visualize more than that. So if rank is 2 dimensions, nullity is 1, then the null space that you see in the plane, it would be just like this line, the column space line or the row space line. Okay. And that is what I actually have that. Let me show it to you.
Sir, so nullity and null space can be used, I mean, we can refer it as the same.
Nullity tells you how much dimension
Yeah.
do you have for the null space, and null space is the space itself. Nullity tells you the dimensions. Now, if you see here in this particular case, rank 2 means the null space would be a line. Now you see that null space is a line, bluish line. Now let me remove the column spaces, or let it be there. Okay. Now you could see that the null space is a line. Now let's say that the rank is 3. Now rank is 3, everything would be 3 dimensional. That's what you could see. But let's say a rank is, do I have the other visualization? I do not have that. But right now, if you see here in this particular case, the rank is 2. So the and this is not the right one. Let me show it to you in the other one. The rank is 2. This is the rank test to basically this is an animation to help you that the
So
entire three dimensional space switches to two-dimensional because those are the only two informations, the unique information that you have. So basically, even though there are three different users, for example, all those users reside on this two-dimensional plane. That's what the meaning of that is. But I do not have that example to show it to you that what exact when the other way around would happen. But I can add that and then I can share that HTML with all of you. Okay.
So, sir, one request. Hello.
Yeah.
So, one request. This looks very. I mean, visually we can realize what is happening with column space, row space. Can you please upload this HTML to that inside
Yeah,
that?
I will. I
So,
will. I'll upload this. Definitely, I'll upload that.
okay, sir. Thank you, sir.
Now let's get started to what we have to do today. This is an interesting lecture for all of us. You will understand one of the things that would go on forever. Uh, when I say forever, what I mean is you would have been using these things for a long period of time without realizing it. And the intuition for that is think of you working on a laptop, right? And there are certain times when you uh, keep your laptop screen aligned with respect to your eyes. What is the reason for that? Does anyone knows why do we actually keep our mobile screens or our laptop screens aligned towards our eyes so that and is there a specific maths thing that we have that we already know because of which all of these things works out well?
Reflections,
Viewing
Re-
angle.
reflection of light.
angle is right. So
So that
reflection is also right. Reflection is all based on angles. But your thought process, yeah, go ahead. Someone else was saying anything else.
so that our eyes will not get stress and strain because of that.
Our eyes is, will not get stressed because obviously because of the angle. If you are not getting enough intensity of light, obviously
The
you will
normal
be
vector
away
of
from
the
it.
plane, right? Basically, it
Right,
points to
the
the line.
normal vector of the
Normal vector
plane.
of the plane, yeah.
Exactly. And that is what is governed by something more profound, which are called as dot products. And this is one of the you will also realize that dot products is generalized Pythagoras theorem. If you get to that intuition today, you have understood most of the parts of linear algebra. If you don't get that intuition today, it's all good. But anyway, we are going to get started easily and just to help you understand from machine learning point of view, understand it as you could have various different types of text, different types of images, different types of things. But if you have to find similarities between them, right? If you have to find documents similar or not, are two different images similar or not, you could just take a simple dot product between them and find out whether what is the similarity score between them just by looking at one single number. Okay, and then we will build more profound idea which is called as cosine similarity. It is derived from the same dot products rule. uh, so the dot product, in a way, are a measure to help us out with the things that we are learning. So go to this particular page. And this is what this explains transformers, the model that we use today in LLM, or let's say, for example, the model which came into being today, which is LLM, the all chat GPTs, Gemini, and all that you're using today. They were made possible, they are successful because we were able to do things in a specific way. When I say specific way, what I mean is there were a lot of background work that people did. And this is attention mechanism. This is just to help you understand attention mechanism, which goes into transformer models. But my idea is not to help you do that. If you see when you go to, let's say, for example, your problem is to predict the next word that would come in the sequence, data visualization empowers users to whatever comes in next, whether it's visualize or create or see. Now, this is the, let's say, for example, this is the entire model for you. Okay. And the entire model, what it does internally is, let's say, this is where all the maths that you are learning comes down to. And that's why I told you whatever you are learning right now today, it will go forever with you because you are decomposing each word as a vector. You see this as a vector, 2304 dimension. Yesterday I told you a vector could be 10 dimension, 100 dimension, or 1000 dimension. So right now you see that the vector is is 2304 dimension, right? And this is the place wherein you are doing the dot product, and this is exactly what helps you understand how similar data is to visualization, how similar visualization is to and so on. So every single place you see that it is just calculating how similar these words are to each other. That is the dot product thing, and this is a very simple idea embedded in a very big model, which are transformer models. So all of these things that you see today, they are just built on smaller building blocks of the idea that you're learning right now, right? So they are not nothing. When after my intention of uh, finishing these MFL lecture is also to help you understand how things are built, right? So after finishing these 16, I generally do not take 16 lectures. It will obviously get extended up to 20 or 21. But after finishing these 20, 21 lectures, you will be able to understand the idea on which these bigger systems like LLMs are built. Okay. And after fifth or sixth lecture, you will generally have that idea because we will finish up with linear algebra and we'll move to calculus. But anyways, let's get started with very simple introduction. Today's topic is more profound. It will help you understand various different types of things. But let's first consider what we have learned till now. Okay. We have learned about vector spaces. And today we are going to learn about inner product, which are generalized way of dot products. Inner products. Okay. When I say inner product, when you combine vector space, basically the place where vectors live, and a way of finding out how similar, dissimilar they are, or what is the distance between them. When you combine them together, you basically can do all possible geometry with vectors. Okay. And that's the most important part of inner product. So you have already learned about vector spaces. Today you will be learning about the intuition about inner products, or the specific version of it is called as dot products. And dot products is what you will generally see everywhere. Whenever you will be talking in terms of machine learning, you will say that let's just take a dot product between them and find similarities between them. If you have two different images, you will have to find out how similar those images are. Just take a dot product between the feature vectors derived from those images. That's how simple things are. But everything we build profound is built on a simple idea, right? Whatever we have built till now. So let's start with a simple vector. Let's say we have a vector x is equals to 2, 3. Now, herein 2 could mean the number of hours. I'll just mute you for some time. I see that there would be some distractions. I did not intended to do that, but I'll have to. Okay. So let's say, for example, herein 2 could be the number of hours someone studies, or let's say one of you studies. 3 could be the number of practice tests that you have solved. Let's say practice test. Okay, number of hours studies, number of practice tests solved. Now, if you, I have to, let's say, for example, this could be your vector on my vector. How many? Let's say you or me, you or I am, both of us are preparing for an exam. This could be your vector. Let's say you. Okay, and X me is something like this. I could have studied, let's say, 1 hours and could have solved only one practice paper. Okay, now how would you find out whether these two vectors XU and XM are similar or dissimilar to each other? Now, the, the more bigger questions are, firstly, how would you find out how big are these two vectors? Two vectors. This is the first question. Second question is, how far is X? How far is XU from, let's say, XM, or how far are you from me, right? And then how similar are XU and XM? And then are there features carrying the same information? Let's say, for example, we have considered these two features, number of hours studied, the number of practice tests solved, right? Are there features which carry same information, carry same information? Okay. Now, the very first question that you see here, how big are these two vectors? This can be answered using something that we are going to learn using lengths. So I will understand the concepts of lengths today, and that's why we'll learn about norms. So all of these norms like Manhattan norm or Euclidean norm, you will understand them today. Second is how far is x and xu and xm from each other. So we'll understand the concept of difference between vectors, the difference between xu and xm, and what is the length between that difference. So you will understand the difference between the vector and the length of that difference vector. Okay, so that you can basically do some sort of understanding of, let's say this is first vector, this is second vector. If I have to find out how far they are, I should have a way to to differentiate them, to take the difference of, let's say, or just do something like this. Let's say this is x vector, this is y vector. How far is x from y? And to understand that, can we find out their length so that we can concretely tell how far they are, right? Because we might not be only looking into also looking from x from z. Let's say there are three different individuals. We might have to find out, are all of them similar, or some of them different, or some of them are, or everyone is very different, right? So we'll have to find out whether x and y are similar, x and z are similar, or we'll have to find out y and z are similar. What is the distance between them, right? Third thing that you see here is how similar are xn and xm, the two vectors that we started with, right? These two vectors, 2 and 3, 1 and 1. Now we can use something called as dot products. So this is what you will basically learn. And dot products, the generalized version of dot products is inner products, which is what you'll learn. The fourth one is, if there are features which are uh, correlated, think of it as, I generally use the simple example, age and experience being highly correlated, and you could see the data like this, right? Now, in this particular case, when you plot a scatter plot, this plot is called a scatter plot. Each of these data points are nothing but a combination, a particular value of age and a particular value of experience. And every individual could have a different age, different experience. That's why you see different values here, right? Now, when you have data like this, scattered like this, you could see that there is some sort of correlation between them. Okay. Are there cases wherein these two features that we are taking, age and experience, are they at all correlated, or they are very non-correlated, something like this? Okay. So the fourth question that you see here are the features carrying the same information. This is answered using something called as orthogonal. Okay. So if the vectors are orthogonal, we would always say that they are different. Sorry, if the vectors are orthogonal, or let's say dimensions are orthogonal, let's say experience is orthogonal to age, it would just be like this, perpendicular vectors. Okay. So if they are in different directions, they would always be, I mean, they are in different directions such that the angle between them is 90 degrees. They would always be orthogonal. In that case, you will see that, let's say this is x vector, this is y vector. In that case, you will all see that x dot y is equals to 0. And why this is 0, which also means that these two vectors are carrying different information. If the features are carrying different information, it makes sense to add more and more different information features in your model. Because if the features are having similar information, they are basically redundant features. They are not carrying anything new to the model. And that's what the concept of rank also relates to. If you are able to connect dots between what we have learned so far, right? So the fourth one would help you understand the intuition of whether the features that we are measuring things with, the features that we have, the columns that you have, right? Are those columns similar or dissimilar in some sense? If they are dissimilar, they should be orthogonal. Okay. And orthogonal means this, the dot product between them is zero. So we will learn about all of these things, but let's go very slowly. Okay. Now, when you, the very first thing that I wrote is length. Let's start with length. Okay. How do you find the length of a vector? Let's say, for example, if, and before going there, why, when I said, are these two vectors similar or not? It's easier for someone to right now assume that what a dumb question I'm asking, right? XU and XM, these two are, let's say, 2 and 3, and the other one is 1, 1. They seem very dissimilar. One way of understanding that is just comparing the number of hours both of them have studied and the number of test paper both of them have solved, because they are very, very different. You will say that the vectors are different. And another individual, some of you might argue the point that if you plot number of hours, number of test paper solved, one vector would lie here, 2, 1. The other one vector would lie here, 3, sorry. Uh, the other vector would lie here, right? So let's say this is 2, this is 1. The other vector would lie here, 3, 1. So, so you would see that they are somewhat similar. Uh, Sorry, 2, 3, not 2, 2, 1, 3, 1, 2, 3. The first vector is, let's say this is 2, and on the y-axis it is 3. The second vector is 1, 1. Okay, let's say that this is that vector. So you might say that, okay, they are oriented in somewhat same direction, they are similar. So the answer to that is, right now we are discussing about two different features only. Think of when we measure, when we work upon uh, any vector. Now think of this, right? What you have done here, data has been decomposed into a token embedding which contains 768 dimensional representation. Now, a vector which is 768 dimensional, let's say, for example, of the vector for XU could look like this, something like this, 0.1, 0.9, 0.6, minus 0.1, and then so on. So there would be 768 dimensions to it. Now, when you have 768 dimensions of which is for first vector, and the second vector is also having 768 dimensions, you cannot just do a simple uh, comparison of how two dimensions are related or how similar they look like, right? You cannot just compare 768 dimension. So you have to have something more, I would say, mathematical or something much easier than that, right? So that's why the concept of these dot products and all have evolved. Now, how big are these vectors? Let's say the length of it. If you have a vector, let's say the same vector x is equals to uh, 3, 4. If I have to find out the length of this vector, the simple idea is, you already know about it. It is all derived based on the Pythagoras theorem, the Euclidean norm or the space that you have, right? So let's say, for example, this is 3, okay, and this is 4. So your vector basically would be here, right? Now you have found this vector. Now, if you have to just say that this is 3 units, this is 4 units, you already are seeing that this is the hypotenuse, and using uh, the Pythagoras theorem, you can directly write that this particular hypotenuse, the length of this hypotenuse as 3 square plus 4 square, right? So the length of this arrow is or the squared length of this arrow is 3 square plus 4 square. So what we write, this is how we actually give rise to the length of any vector. So what we do is, using the simple Pythagoras theorem, you find out what how much the component of y is there, how much is the component of x is there, or whatever, both of them are two different components. You square them up because they all aligned well in a right angle triangle. So now you are able to find out the length of this particular vector. Similarly, you can find the length of any other vector, right? Now all of these lengths are described like this because these are square distances. The way of representing this is called as Euclidean norm. Euclidean norm, okay. Or people call it as 2-degree norm, or some people call it as Euclidean norm. But if you see something like this, it means that it's a length of the vector, and it means that it's a Euclidean length. Okay. Now, to find Euclidean norm or Euclidean length, you can just do this under root of 3 square plus 4 square. That's what you just saw, right? Or you can write it like this as well. This is the squared form of that. So the squared Euclidean distance is equals to 3 square plus 4 square, which is what your Pythagoras theorem is, right? Now you can generalize this concept. You can say that right now you have two different dimensions only. You are measuring the vector with only two dimensions. Let's say the number of hours studied per day, the number of test papers solved, the number of calories intook, and then so on. There could be various different dimensions. So you can actually think of the Euclidean norm as a generalized length written down as x1 square plus x2 square plus and so on plus xn square, right? This is how you can simply generalize. Now, the mathematical intuition of this is the squares. The reason that we have squares here, think of it as the squares, they they avoid cancellation, because if there are some negative values, you know that they will get to positive. Okay, the sum accumulates the contribution for each coordinate. So think of this is this contribution coming from the first coordinate. This is the contribution coming from the second coordinate, right? So let's say 3 and 4 are the vectors, or 5 and 6 and so on. This is what the vector is. So this is the contribution coming from first, contribution coming from second, similarly contribution coming from the nth, right? Now, when you define vectors with the length of the vectors like this, you have to understand that length behave in a specific way, right? You cannot have lengths which are negative. You cannot have a length which are distorted. I mean, in Euclidean space at least, you cannot say that the length are like this, right? So they have to be linear. They have to, whether you are, let's say, for example, if you are traveling from A to B, when you travel from A to B, if the distance is 70 kilometer, then if you travel from B to A and you take the same path, the distance has to be 70 kilometers. It cannot go 80 kilometers. So there are certain things that you will have to keep into your mind when you compare these distances. Now, the first thing that comes up is, and these are called as the norms, the axioms of the norms. Now, the norm is nothing but the length, right? So I have not just told you about it. When you see the word norm, just relate to it as length. People are talking about length, and there could be various different types of length that they could talk about. There could be Euclidean length, Euclidean distance. There could be Manhattan distance, or Manhattan norm. Okay, Manhattan. Or there are various different types of other norms that people have used, but we'll stick to this because these are the two different things that are used more, uh, or they are used more oftenly in machine learning than all others. So we'll stick to Euclidean norm or Euclidean lengths, Manhattan norm or Manhattan lengths. Okay. So now, when I say you have distances between A to B is similar, or let's say, for example, they have to be linear, there are certain axioms that these norms follow. And these axioms are, and that's what you would see. The reason that I did not start the way I could have started is, if you'll when I looked into the slides yesterday, I was seeing the slides and found that, I mean, because of the after the lecture, I looked into the slide and found that the way it is represented here, if I would have started, a lot of you who are already finding this difficult, it would have gone in a separate dimension altogether, right? So I thought I'll not start in that direction. I'll go slightly slow. But anyway, now when you look into the length, like say this tells you the length of the vector, right? And now I'll not write it like this. I'll come back to you, Harshad. When yeah, I'll come back to you in 15, 20 minutes. Let me first at least cover the first part, which is the length. Okay. So uh, the length of the vectors can never be negative. So the first norm is the length should always be greater than equals to 0. If the vector is 0, the length would be 0. If the vector is non-zero, think of it as in two-dimensional coordinate system. If the vector is not at origin, if the vector is somewhere, there has to be some positive length, right? So the first norm is the length is the first axiom is the length has to be non-zero. The second axiom is if you scale the lengths, okay, let's say for example, if you scale the vector. Now, if you see here, let's say if you have a vector x, you already know when you scale that vector by a positive number, it will get like this. It will get scaled like this. If you multiply it with a negative number, it will go in the opposite direction, but it will stay on the same axis. That is what we have been discussing so far. But if you scale the vector and then take the length, it is almost similar to just scaling the length of the vector. Okay, you take the length of the vector and then scale it independently. So this is the second axiom that you have. So if you want to calculate the length of a scaled vector, you can also do it like you first calculate the length of the vector and then multiply it with the scaling factor. Okay. The third norm is, the third axiom is if you add two vectors and then take length, okay, that combined length between them has to be less than equals to the length of vector x and the length of vector y. Okay, and this is the triangle inequality that you all would be knowing about, right? So let's say, for example, if you have x here and you have y here. So if you add x plus y, the length of x plus y has to be less than equals to the length of combined length of x individually and the length of y. And that's what you see here. Okay. So the combined length of x plus y is equals to the individual length of x is less than equals to the individual length of x and individual length of y. Okay, and this is a combined vector that we are talking about. You already know that we can add vectors when you have two different vectors. Let's say this is first vector, this is second vector. When you add, this is a third vector. So if you have to restrict some applications on the vectors that it is made from, you will just say that the length of the resultant vector would always be less than equals to the length of the vectors it is made from. That's what the intuition is. So if you add two things, the output is not going to be the more than the individual contribution. That's what that means. So these are the three different axioms of lengths. This is what is called as length. Now, there are two different types of lengths that we have. One is simple Euclidean, and the second is Manhattan. Okay. And the Euclidean length is simple, what you see as a squared length. Let's say, for example, you have this two-dimensional plane and you have the vector here. The Euclidean length is just a direct taxi from origin to that point. So the direct way from there. Let's say, for example, a bird flies from origin to that point. That is Euclidean distance. While Manhattan distance is, you get to see how much that point is in x direction. Okay, so how much is that point in x direction? You will first go to that, and then how much is it on y direction? Okay, so the Manhattan norm, basically, let's say, for example, this point is 3, 4. In Euclidean distance, you will just be doing if you have to find out the length, you will just be doing 3 square plus 4 square. In Manhattan, you would find out how much it is in x direction, which is 3, and how much it is in y direction. Okay, so this is just 4. So this is what you will be having in Manhattan. So Manhattan distance would be 7, and whatever it is, 9 plus 16, 25, it would be 5, right? Both of them are valid. It's just that sometimes majority of the cases, 99% of the cases, you will see that we'll be sticking to Euclidean distances. Now, why are these things important? The reason for that is, if you know the length of the vectors, let's say if you know this vector is long, if you know this vector is short, you would at least have some way of comparing whether the vectors are long enough or short. Some vectors are shorter, some vectors are longer, and you would have some way of comparing them, right? So that's why it is important. This is the first topic that we wrote on the board, which was length. Now we will go into distances. Now, before going into distances, let me unmute. Some of you are raising your hands. Let's see what is that question. That's right. This is really, really good. But anyways, ask your question. Go ahead. I saw some of you
Okay,
raised your
okay,
hand.
sir. I'll go
Go
first. I was waiting for Harshad actually. So, sir, like I
ahead.
have two questions. So, one is when we are getting the length. So, shall we always consider from origin, or it could be length between two vectors?
The If you think of it as when you talk about in length of one first vector, it has to be always from the origin. Okay. Once you have computed the length of the vector from origin, you can always find out the length between them. Now, there are other things that you will have to learn about, but you will eventually see that the length between the difference between these two vectors, either this is x vector, this is the y vector. If you have to find out the difference between these two vectors, x and y vectors, and what is how far basically they are, you will have to find out how the length between the difference vector, right? So this difference vector, this is what you will eventually see that how that formula spans out and uses dot product today. So you'll be able to understand that, but I haven't got to that point. Once your first thing is, if you are comparing length of one specific vector, you will have to have some point from where you would see that length as, and that point always is from origin. Okay. But when you are seeing how far those two vectors are, you would have to establish some notion. And that notion is what you will get to when we will discover about the other things. Okay.
Okay, sir, understood. Sir, other follow-up question was like in the exams you have mentioned, right? The length should be greater than equals to 0. So,
Right.
so do we need to consider 0 also because we are trying to find length of a vector to compare against some other vector. So, what is the significance of 0 length here?
There could be some you will understand that there are certain cases wherein the vector could be all zero, and this is where you will soon understand the sparsity in the matrix. Okay. You could have a case wherein, let's say, for example, there could be two different vectors and one vector is all zero. And there, in machine learning, you will understand in your classes on machine learning, you will eventually understand that there are cases when you would result in certain vectors which are all zero, which have components, all zero components. And when you have a zero vector, you would have it doesn't has any length. That's why you have to have that consideration in place, that zero vector doesn't has any length.
Okay, sir, understood. Thank you.
Yeah, go ahead. Next.
Hello, sir.
Yes, yes.
Sir, can you take the second point, the scalar, what you mentioned on that?
The
Explains.
scale.
Second point.
Yeah, yeah, yeah.
Yeah, the scalar, can you explain once? Like,
Yeah, scalar is, let's say, for example, when you have a vector, let's say this is x vector. When you scale that vector, what happens is it gets scaled up, right? It goes to the some other point. Basically, it stays on the same axis, but either it would get elongated or it would get diminished, but it will remain at the same axis. It can also go to zero if you multiply the scaling value lambda is equals to zero, right? If you have lambda is positive, it will grow its size. If lambda is negative, it will go in the opposite direction, in this direction, right? Now, what it says is if you scale a vector, and then let's say, for example, this particular vector was A, this is where it was initially, then it might have moved to a new point. Now, because the vector has moved to a new point, then the length would have changed, right? So the length of the scaled vector is equals to nothing but find the length of the initial vector and then scale it. So you don't have anything specifically for scaling doesn't has any length. So a scalar unit doesn't has any length. So what it says is when you scale a vector, the length of that vector is equals to find out the length of the original vector and multiply it with how much amount you have scaled that vector as, right? So that is how equivalent it is. Good.
Yeah, okay, sir. Thank you.
Yeah.
Uh,
Yeah.
Sir, I have a question. So here, I mean, every time it is not 90-degree, right? It can be any angle.
Which case?
I mean, you said Pythagoras.
So
So
think
in the
of it
second,
this in this particular case. Let's say, for example, here when you see any vector, okay, it would always pick up a right angle triangle. Think of any other vector. Think of any other vector wherever it is. It would always pick up that right angle triangle. So that Pythagoras theorem is always applicable there, and that's why you have that Euclidean distance formula, the way it looks like. It would always be perpendicular. Sorry, it would always be right angle triangle.
okay, and on the third, I assume what you explained, the combined length, it should be less than the individual length of vector, or is it? I mean, because here the example we have 3, 4, and the combined length was 5. So it is not less than individual, right? It is the combination of that, right?
So think of it as when you have the first vector, think of it as when you have the first vector, let's say 3, 4, and the second vector is 1, 1. Okay. And now the 3, 4 has its length as 5. Okay. 1, 1 has its length as root 2. So the combined length is 5 plus root 2. Now, if you add these vectors, you will get to 4 and 5. The length of 4 and 5 would be under root of 4 square plus 5 square, which is what
Okay.
16 plus 25, 41. So the under root of 20, 41, what it's saying is square root of 41 has to be less than equals to 5 plus root 2. That's what this is combined length. The combined length of the vectors, when you add the vectors, the length of the added vector has to be less than what it is originally made from.
Okay.
Next
But so
question.
in the case of Manhattan, like norms, it would be same always, right?
Yes, that is we follow different principles there.
Mm.
That's right.
Sir,
Now,
go ahead.
go ahead.
Sir, I have a question on far versus similarity. When two vectors are far, doesn't that obviously mean that they would not be similar? Why is it like two different questions that we look for?
Okay. When two vectors are far, you have to have some notion of quantifying far. When you say far, are they separated out by some angle, and that angle could be, let's say, 30 degree, or they are separated out by an angle which is 90 degrees, let's say, or whatever, right? So when you say far, are they far separated out by certain angles, or they are far when they are inclined in certain angle? Let's say, for example, the angle between them is zero. Basically, they are collinear. They are scaled from version of each other, right? So they are similar. Their length could be different, but they are similar because they are pointing in the same space. Think of it as you have a news article, okay, and the news article has um, let's say that you have newspaper on, and newspaper is talking about PM Modi saying that do not buy gold and all, right? So, and then there is in shorts, the shortest platform, or let's say on Twitter, you found someone writing in, let's say, 14 different words about the same thing. Now both of them are conveying the same meaning. One is a longer format, the other one is a shorter format, but the meaning is same. You have to have certain mechanism in place to find out the meaning that they are conveying is same. So are they pointing in the same direction, or they are pointing in different direction? If they are pointing in the same direction, it means that their meaning is at least same, though the vectors could be different, the length of the vectors could be different, because the first one is actually telling you the entire story in much detail, the second one is telling you the story in shorts.
So
Right.
that's the length, right? It is
Right.
overlapping, so dimensions are same. Actually, at least their magnitude is different, right? But
Right.
then
That is
far
different.
far versus similarities, right? That's what was confusing me.
Yeah, okay. Far is how far that, let's say for example, when you say far could be all based on how much angles that they are apart. And
Yep.
when the angle between them is smaller, it means that they are very similar. If the angle between them is
Okay.
larger, it means that they are very, very dissimilar.
Okay.
Okay.
Sure, sure. Makes sense. Yeah. It's relative to angle, how deviated they are from each other.
Right. Right.
Okay.
Right. Yeah. Next. Okay. Gushal, we are good.
Sir,
Sir,
I had a question.
Yeah.
next.
So when you have calculated Manhattan, this also means how far they are from the origin, right?
Right. That is right.
Right. And we are taking the modulus of the distance, but in Euclidean we are taking the square of the
Square of the distance. That's
distance
right.
from the origin. And
That's right.
second, sir, yesterday we studied in machine learning that great about the gradient descent, and we noticed that we have to keep running the algorithm until we reach the point of convergence, and there also we calculated distance when the error was within the limit we have set for. So there also we use the similar formula. So this is related to that when you have calculated the norm of the vector.
The norm of the vector gradient
Mm.
descent formula is they are, let's say for example, vector wise they are similar, but because the concept of vector, we are basically in gradient descent. What you're doing is you're saying that W new is equals to W old minus alpha times the gradient of the loss with respect to the weights. Right. So that's
Yes.
what you do. Basically, there is a vector, there is a first vector, and there is a second vector. So you are basically differencing them. So this is a vector minus b vector. That's what you all do. This is the scaled b vector. dl by dw would be of the same dimensions. You will eventually learn that. So you are taking first vector and you are differencing it with the second vector. This is actually, the concept is similar, but we are looking into how, let's say for example, how much should we move, how much we should we move away in gradient descent. What we do, we start from a particular point, and then we say that in which direction should we move, so that we should either ascend or descend. Because it's a descent, we'll have to descend, right? So it says that from your initial point of origin or wherever you started, how how should you go descending? So in what direction you should descend and how much do you descend? Let's say for example, gradient descent tells you the direction. So it is derivative dl by dw, the partial derivative. It tells you the direction, in which direction you should move, right? And how far you should move is what alpha, how much do you want to eliminate or separate the second vector from the first one. So first vector is that point. Now how far you move is the difference from that point, right? So that's why you are taking a vector minus b vector in the concept of gradient descent. It's almost similar, but they are slightly different. By the way, gradient descent is also one of the topics that we will be going through. So you don't have to worry about gradient descent. Is one of the topics that I actually teach with immense pride, because I have done a lot of research on that. So you will have much better understanding of vectorized form of gradient descent. So we'll discuss that in that lecture.
Okay, sure, sir. Thank you.
Okay.
Hello,
Now,
sir. My
yeah.
next last question is, as you said in first axiom that the length has to be non-zero, right? And in your notation, you said you actually said that x is equal to or greater than zero. Why it is written like that?
X is so length is non-zero first. X
Yeah.
the length has to be greater than equal to zero. Non-zero as in non-negative. I could have said wrongly, but what I meant is the length
Okay.
can never be negative.
Okay. Never be negative. Okay. Okay. You said non-zero, so that I got confused. Okay. No problem.
Okay, got it. Okay. Now
Sir,
let's
we have a two lengths like Euclidean and Manhattan, right? No, two
right,
norms.
right,
So
right,
suppose one person is using Manhattan, right, for solving particular problem, and
right,
another person is using Euclidean length to for
right.
solving one particular problem. So output would be different, right?
Yes, yes, but you have to stick to one. If you are solving a
Okay.
problem, you have to stick to one. If you have to have a parallel level playing ground for all the vectors to be evaluated on that in that playground, right? So you have to stick to one and then see how does it comes out to be.
Okay.
Okay,
Okay.
let's get to the next topic. Thanks for all your questions. I'll see all of these things that you have written down and we'll respond back later on. Okay. Okay. Now. Okay. Now, one of you, I'll get back to you, Namsta. I'll after this because we have to finish some of the things which are very important. Anyways, I have already deduced orthogonality from here from these topics, but I have to at least finish some of them. So let's say that you have two vectors, one, two. One, the very first question that someone asked was about the same thing that we had to go through in the next. So let's say we have two vectors, x is equals to 1, 2, y is equals to 4, 6. Now, if you have to find distance between them, or let's say for example, distance of between x and y, you can just write it as distance between the length between the difference between the vector, right? So if you have to write x minus y, you can just take 1 minus 4, which would be minus 3, and 2 minus 6, which would be minus 4, right? So this is the vector that you have. X minus y vector is minus 3 and minus 4. If you take the length of x minus y, the length of x minus y in this particular case would be minus 3 square plus minus 4 square, which would come down to be 5. Now, distance is now what we did. We said that distance between x and y could be just the difference between the two vectors, these two vectors. And when you say distance difference between the two vectors, and you can take the length of the difference, which is basically telling you how far, in some sense, these vectors are distant apart. Okay. So right now you are saying that these two vectors are 5 distance apart from each other. Okay, there is some sense of finding out how close, how similar. Let's say if this would have been 0, we know that both of them are actually the on the same axis, or let's say on exactly at the same point, not on the axis even. They are exactly the same vectors. If the distance is 0, if the distance is non-zero, it means that they are slightly far away from each other. And if the distance is larger, if this value is larger, you will know that they are more far away. Now this is where these things is what you will use in things like k-nearest neighbor. These are the things that you will learn. This is one of the machine learning algorithm, one of the simplest algorithm that you have. And if you have to go into it, let's say for example, go to animatedml.com and then point. This is go to supervised learning, and within supervised learning, you have k-nearest neighbor. Now you see that this is each of these points are vectors, right? Now you are trying to find out, look at these blue points. Sorry, the teal blue color, right? So if you see the distance between each of those points is highlighted in that color. Now, when you are here, how far each point are, when you are here, how far each points are, right? So when you are here, you are just finding out if a new data point would have been here, how far that new data point would have been from these two different types of classes. So you have the blue classes and red classes. Let's say these are people who have low BP, these are the people who have high blood pressure. And let's say that there is a new individual who comes in here with a particular age, with a particular weight. You are trying to quantify whether that individual would have a BP problem or not. Now you have found that once first you found how much far that point is from five different vectors, because we in KNN we choose how many nearest neighbors do you want to find out. If the value of k is 5, you are just finding out five nearest neighbors from that point. Now you found that two of them are actually low BP patients, three of them are high BP patients. Because the majority of them is high BP, you will say that it's a high BP. So this is the algorithm, but the algorithm itself is highly dependent on the notion that we just established, right? Which is distance. How far are the data points, or how far they are from each other? And just to find out the distance, if you know this point, if you know this point, take the difference between them and then the length. So you'll know what exactly is the distance between them. And that's what we looked into there. Similarly, in clustering, if you do clustering, this is the concept that you will learn eventually, or you might have already learned. Clustering is bucketing of similar data points together. And when you say similar data points together, you might have a situation like this, or you might have a situation like this, right? So how would you say that these data points are very similar? This group is very similar. You would have to have some notion of finding that the distance between, let's say, sorry, the distance the distance between these 2 points versus these 2 points, this distance is larger than this distance, right? Because this distance is smaller, you know that they all, or all of them, are actually very close to each other. While because the distances between the groups, they are larger, you know that they are far away from, but there are more intuition that you will be learning in clustering. So that is also based on distance. Similarly, embeddings. Let's say, for example, if you have different texts, right? When you have a text like "I love my country," and when you have a text like "I like um, books," whatever, right? Let's say, for example, these are the two different texts. Now, how far these two texts are similar to each other or dissimilar? Firstly, you will have to represent. You might have been seeing at these different embedding models, right? And these embedding models are nothing but representation of each of these text in some vector space. Okay, and that vector space could be 768 dimensional, or let's say 1000 dimensional, or whatever dimensional, right? So if they are 768 dimensional, you would represent first vector with 768 dimension, second vector with 768 dimension, and they might look like this. This is first, second, third, fourth, fifth, and then 768 dimension. This could be point 1, point 2, and then so on, right? Similarly, the second vector. And then you can find out the distance between them, how far they are, how close they are, so that you can get a sense of similarity in terms of distance. Okay, and that's why these are important. Now, when when you have distances, you can actually use something more profound, and that is what, let's say, distances tells you how far apart they are. But there is something more profound than just measuring distances, and that is called as dot products. Now these dot products are, let's say, for example, if you have a vector x, let's say that that vector is 1 2 3, and a vector y, and that vector is 2 4 6. Obviously these two vectors are scaled version of each other. You can see that the second vector is twice of the first vector, right? They are in the same direction. You already know that, let's say, in the three-dimensional space, you will have the first vector and then the second vector on the same line. So this is 1 2 3, and this is 2 4 6. Now these two vectors are in the same direction, but if you have to find out how similar they are, there is a notion of finding similarities, which is governed by dot products, and dot products is defined via this way. Let's say, for example, you write it as x dot y, or you write it as x transpose y. Writing them like this is the same thing. What I mean by both of them is, think of it as X dot Y is nothing but taking the product of the same dimensions and adding them together. So let's say, for example, when I write X dot Y, I would just be doing this 1 into 2 plus 2 into 4 plus 3 into 6. And the output could be what? 2 plus 8 plus 18, 28, right? So the output is 28. But right now, X dot Y, I have found out is 28. Whether X transpose Y is the same thing or not. Let's say in the matrix multiplication form, you would write it as X transpose would be, if you think of it as, it would be the same thing, because right now what you have is, think of it as 1 cross 3 vector. Okay, 1 2 3, and then you would have 3 cross 1 vector, which is 2 4 6. Okay, now you can multiply them, 1 cross 3 vector with 3 cross 1 vector. You would, when you multiply them, you will get one value, which is 1 into 2 plus 2 into 4 plus 3 into 6. It comes down to be 28, right? So both the versions of dot product is written like this, X dot Y, wherein you would be multiplying the same dimensions and adding them all together, and you will eventually get a particular value. Now what dot product does is, you have vectors. Dot product, when you take dot product between two vectors, it gives you a scalar number, a particular value. Now there are problems also associated with it, but there are also certain good things about it. If the dot product, think of it as, if x transpose y, if x transpose y is greater than 0, right? It means that they are somewhat similar, they are somewhat aligned. Okay, if x transpose y, or let's x dot y or x transpose y, they are all same, right? If x dot y or x transpose y, if this is 0, then it means that they are not aligned. Basically, they are all, you will eventually see that when x transpose y is equals to 0, they are orthogonal. Basically, they are you get that idea. But if x transpose y or x dot y is equals to, or let's say is less than 0, then they are basically in opposite direction. Opposite direction. When they are aligned, it means that they are in the same direction. Let's say, for example, these two, when you take the dot product between them, they are aligned in somewhat in same direction, right? When you have a vector like these two, when you take dot product between them, the dot product could be negative, and because the dot product is negative, it means that they are aligned in different directions. Okay, so this is what the meaning of dot product is. If the dot product is positive, they are somewhat aligned. If the dot product is negative, they are not at all aligned. If the dot product is less than 0, they are in opposite directions. Okay, now you can simply write dot product as x transpose y, which is nothing but summation of xi yi over all I. This is how you generally write it, right? The formulation of it. Now, the simplest thing that I have just told you, just to give you the same idea, if the first vector is positive, the second vector is positive, the dot product would be positive, right? If the first vector is positive, the second vector is sorry, let's say that if the first vector is negative, second vector is negative, then the dot product would also be positive, and that's what you will eventually see. If the first vector is positive and the second vector is negative, or first vector is negative, second vector is positive, the dot product would be negative. So the dot products adds up whether you have similar agreement or not. In these two cases, if you see here, both the vectors are in the similar space, both of them are negative, they are agreeing to each other. So dot products adds up agreement and disagreement across dimensions. If you think about what you are doing, all the dimensions that you are doing, let's say, for example, x vector is written as 3 4, and y vector is written as 5 6. So what you are doing, you are just adding the agreement that you have. Let's say, for example, the agreement in the same direction, how much do they agree in the same direction, or how much do they, let's say, for example, the value would have been 10 and minus 2, how much do they disagree in some other dimensions, right? So what you're doing is, you're kind of adding up agreements plus disagreements together. That's all you are doing. There could be some dimensions wherein the vectors could be disagreeing, some dimensions wherein the vectors could be agreeing as in almost in the same, some values could be here and there. Let's say for example 3 5 versus 3 and minus 5, right? They have a similar agreement. On the second dimension they have a different difference, right? So it adds up agreement plus disagreement, because eventually what you do is you do 3.3 plus 5 into minus 5, right? That's what you do. So you are adding agreements and you are disagreements together, and that's what dot products do. Now, in connection to machine learning, you might have already looked into it. You might have looked into linear regression, right? Which is of the form W transpose X plus B. That's what you do there. So if you have a weight vector, you have X matrix, you have a weight vector, you generally take a dot product between them and then you add the bias term, right? This is what the equation of the line is. Y is equals to W transpose X plus B. This is what you use. So you have weight vector being taken as a dot product with the input matrix X, right? And same goes in if you think about neural networks. So if you have already gone through it, neural networks also does the same thing. You have let's say for example you have neurons here. Okay, whatever data comes in at each one of them. Let's say the value is 2, the value is 4, the value is 6. You will have weight attached to each neuron. So weight and biases. Okay, so these weights and biases, what you're doing is you're just taking a dot product of weight with whatever input information is coming and then adding bias there. So in neural networks also you are doing the same maths, W dot X plus B or W transpose X plus B, right? So in linear regression, you are doing the same thing. Neural networks, you are doing the same thing. And then that's why I said, this is dot products is what you will be seeing all across in ML, everywhere. Okay. Now, if you have got this idea, the dot product is also represented like this. Let's say, for example, X dot Y is also represented like, or let me not get into that. Let me first write you the inner product. Okay. Now, when I say dot products, X dot Y, you can also write it as, think of it as, uh, you can you can also write it as, or let me think of how can I explain it to you in a much better way. Uh, so think of it as X dot Y can also be written as X transpose Y, which can also be written as X transpose I times Y, because identity matrix, you can also see that as X transpose 1 0 0 1, and then you have Y vector. You have first vector X, then you have a matrix I. Okay, let's say that these are all two-dimensional vectors. Okay, two-dimensional vectors as in let's say 3 4 or 5 6. These are the two vectors, right? So let's say that this is how it is. Now you have X transpose multiplied with the matrix multiplied by the vector Y. Now it's all of them are the same things, right? If you will do that, identity matrix does nothing. So it will not have any effect. But think of it as, if I replace identity matrix with something else, X transpose, let's say AY. Okay. This entire dot product changes to something new, which is called as inner product. And this is generic generalization. You moved from X dot Y to X transpose, or X transpose Y to X transpose IY, from X transpose X transpose AY. And then what you do is you overlay some conditions. What could be A? Okay. Then you say that A can only be symmetric. You already know symmetric matrices, right? What are symmetric matrices, guys? What are symmetric matrices? A is equals to no SQ, A is equals to A transpose. That's right, right. So let's say, for example, if you have a matrix like this, let's say 10 0 0 1. This is a symmetric matrix, because if you think of this is A, and if you take its transpose, the symmetric symmetric is in if you take the transpose of this matrix, transpose as in changing rows to columns and columns to rows. Now, if I take the first row and change it to column, I would get transpose as 10 and 0, right? And then I take the second row and make it as column, I will get 0 and 1. Now, if you see both the matrices are same, right? So A is equals to A transpose. That's what is symmetric matrix. So we say that as long as A is symmetric, and second thing is as long as A is positive definite. Now, this is something that most of you might not be even knowing about. What do you mean by positive definite? Anyone knows about positive definite matrices? Does anyone knows? No. Okay. Good, good. That's actually important that you don't know about it. Determinant is greater than 0. That's right. Some of you actually know about it. That's right. Positive definite matrices have an important. Harshad, can you type your question, Harshad? I mean, it will. I see that you have raised your hand. Let me take this question. I see that he has been raising hands for some time. Yeah, Harshad, go ahead. But this is only one question that I'll be taking. Go ahead.
I think it's by mistake, sir. I guess from his end.
Okay. Thanks. Then let's get into this. See, positive definite matrices are these positive definite matrices are more important in the entire machine learning. You will see that the concept of convex spaces. Someone just discussed about gradient descent. If the space and the graph that you are doing, or let's say the path that you are walking on, if you are walking on a mountain and the mountain does have things like Pangong Lake. How many of you have gone to Leh, right? So Pangong Lake like area is like this, right? So you have certain situations wherein the mountains have a void, and water which gets on as ice on the mountains, it gets accumulated like lake. So you get things like Pangong Lake, or we call it as local minimas, right? So Pangong Lake are kind of local minimas in hilly regions. So when you have a situation like this, you will get trapped to a local minima. Let's say, for example, if you roll a ball from here and you would want your machine learning model would want to minimize the error, right? So the minimum error is somewhere here, which is global minimum. Now, let's say, for example, this is error, right, on y-axis. If you roll a ball, if you start learning your algorithm from, there are chances that your ball or the marble would get stuck here. So if you have to reach to the minimum most point, you would have to ensure that the surfaces doesn't has those minimums, right? The convex surfaces, convex, this is what you will learn in machine learning and even in 7th, 8th lecture today, sorry, in MFML as well. If you have a convex surface, or let's say not 7th, 8th, 9th, 10th, I think, yeah. So when you have convex surface, if you roll down a marble, it will eventually go towards the, the, the minimum most point, right? Positive definite matrices guarantees that the graph that you're looking at or the machine learning feature space that you are working on, it is convex. So if the matrix is positive definite, the surface would be convex. This is you will get more idea about it, but this is why these matrices are important is because they give you great good geometry to work around. Okay. And the second thing is why are we discussing in terms of inner product is if you think about positive definiteness, we also have linked something like this in dot products. Sorry, in when we were discussing about scaling of vectors, right? So, or taking the length of the vectors, we said that the length of the vectors could never be negative. Now, here also, positive definite matrices, what they do is they ensure that whether you are measuring the lengths or you are measuring similarities, the similarity measurement based on a positive definite matrices, they cannot, let's say for example, the length that you are measuring, right? They can never be negative. They can never go in a direction wherein you are saying that that the distance is -2, -4, -8. So that's why positive definite matrices are important. Now, what is the essence of it? Think of it as you have a matrix like this, the same matrix, let's say 10, 0, 0, 1. By the way, this is a positive definite matrix because the eigenvalues are positive. You will learn in the next class. And also the determinant is positive. You see the determinant, you find the determinant 10 into 1 minus 0, which is 10, right? So determinant is positive. And also the eigenvalues are positive. Now, this positive definite matrix, what it does is, if you have a vector, let's say x, okay, and you multiply that vector with this matrix, what would happen is that vector would get scaled. Now, if you look into this 10, 0 and 0, 1, the reason that we have 10, 0 here, it means that, let's say for example, uh, this type of matrix, the kind of transformation that it does is like this. Let me show it to you what it does. So think of not 10, 0. Let's say that I do not have a way of doing 10, 0, but let's say it is 2, 0. Okay. And 2, 0 and 0, or let's say 2, 0 and 0, 1, right? So let's say that 0 and 1. So this is that. Now, if you see here, the kind of transformation that this matrix does is this. This is the kind of transformation. See that one complete block moved twice, right? Say this particular line was here previously. Now it's kind of like you are holding a spreadsheet, sorry, a piece of paper and then stretching it horizontally, right? And that's what happens. It gets elongated from these sides. So this is the kind of transformation that the matrix does. Now, because of this transformation, what would happen? Let's imagine a vector there. Let me see if I can place a vector. Yeah. Now you have a vector here, V. Now, because of this matrix, the vector has moved to this new point, right? Now, if you take the dot product between the original vector and the moved vector, okay, you would see the dot product between them would always be positive. And that's the essence of this positive definite matrix. Positive definite matrix, the kind of transformation that it does, such that when you take, let's say, for example, when you have a vector x, when you move that vector by transforming it, by multiplying it with a, this vector, the resultant vector would be y. Y is equals to ax. Now, when you take the dot product between the resultant vector and an actual vector, right? Let's say x dot y, this is guaranteed to be positive. And that's the essence of positive definite matrix. Okay. So this is what positive definite matrices does. But all of that you will be looking into is all related to the notion that you will be learning in maybe next few classes. So just stick to that thought that positive definite matrices are important. And this is one of the important measures, or this is one of the important criteria for the inner product to behave properly. And when I say inner product should behave properly, the positive definite matrix, so sorry, the matrix A, remember where we started from. We started from x dot y. We moved to x dot y to x transpose y because they are same thing. And then we said that we introduce an identity matrix in between them. That's also same thing. But when the identity matrix changes to x transpose ay, okay, then you are saying that what kind of matrix A could be such that the dot product, they do not behave very differently. A has to be certain type of matrix such that the distances remain positive, such that the distances, let's say, for example, when you take the inner product between, this is how you write inner product, by the way. When you have to write dot product, you write it like x dot y, but you have to write inner product, you write it like this. When you take inner product between two vectors, or let's say first vector with second vector, and you take the inner product between second vector and first vector, they has to be essentially same. Now this matrix A, the symmetric positive definite matrix, ensures that symmetric positive definite matrix ensures that they actually behave like this. Okay, so it means that it follows three different criteria. Then those three different criteria are positive. Let's say the distance is being positive, the distance is being varied based on certain linear properties, and that's why we say that whether you measure, let's say for example, when you go from point A to point B, whether you measure the distance from point A, let's say from A to B, it is 70 kilometers. B to A, if you are following the same path, it has to be 70 kilometers. So it is bilinear in both the ways, whether you measure the distance from A or you measure the distance from B. It is bilinear from both the cases. Okay, that's why the assumption of bilinearity comes in. Third assumption is it has to be positive definite because there is symmetric, positive definite, and then there is linearity. Now, what we are saying in symmetric is the matrix has to behave. Why it is symmetric? Because the matrix has to behave properly, such that whether you take inner product between x and y or y and x, it has to be same, right? Positive definite because whether you take distance from a particular point, let's say distances can never be negative. That's the idea that I wanted to tell you. Third is whether you measure distance from A to B or B to A, it has to be the same thing. It has to be linear. It cannot change because they basically are in the same space. Whether you measure distance from x to y or y to x, the distance is not going to change between the vectors. And that's what is bilinearity. Okay, these three things are taught very differently in your slide. Do not get confused by the notion that the way they have written it down there, because they don't mean a lot. When you go through the slide, you might find that difficulty in going through it and understanding it. So let me show it to you. This is that. So let's say, for example, this is what we already have gone through, but this is that part, the bilinear mapping. Okay, it says that when you add two vectors and you take the inner product of it, let's say for example, when you scale the first vector, scale the second vector, and this is the scalar multiplication and vector addition part, the first part. And you were saying that when you scale vectors and take a dot product with the third vector, okay, the the inner product of the, let's say for example, this particular thing that you are seeing here, the inner product is almost equal to scaling the inner product between the first and third vector and scaling the inner product between the second and third vector. So this is the first part. In the first part, we are first scaling the vector and then taking the second and the the inner product. While in the second part, we are saying that we we would scale the other vectors, let's say for example y and z, and then take the dot product with x. So herein we are first scaling the first vector. In the second one, we are scaling the second vector. It has to behave similarly. It has to behave in the same way. It cannot be like when you are scaling the first vector and not scaling the second vector and taking the inner product, it would be different from what it is. So that's why you see on the right hand side, the things are same. Okay. The idea there is, if you have to consider distances between certain things, they have to be some similar things. When you have vector A being measured from vector B, the distances between them has to be similar. Then the third property that is written down here, if you see here, it has to be positive definite, which means go negative. And that's what you see. If you have zero vector, it should be zero. If you have a dot product with, sorry, inner product with itself, it would always be positive. If you have inner product of a vector x with y, it needs to be symmetric. And this is the symmetric property that we just talked about, right? So all of these things which are written down here is nothing different from what we're discussing. It's just that the abstraction that the slide brings in, which makes it slightly difficult to understand. Okay. Now, machine learning connection to all of this is, there are certain times you already know that certain features are more important than some other features, right? So let's say, for example, if you are trying to predict salary of an individual using features like age and experience, or number of certificates that they have done, salary might be more important. It might be more important for you to predict salary based on the AI certification someone has done, right? So it salary could be more predictive based on the number of AI certification, the number of AI courses someone has done, right? So if in that case, you might want to give more importance to certain features, and that's why you take into account a matrix like this 10 0 0 1, because you are saying that, let's say for example, this is your first feature. You are saying that I will give more importance to the first feature than to the second feature, right? And that's why you saw that the first feature expanded. So these matrices, they are just used as a measure of putting together importance to certain features in the entire space. Okay, and there is no consequence, or there is nothing more important than we just discussed. I'll take a glass of water. Give me 5 minutes. I'll take a maybe I'll take a break of 3 4 minutes, and then I'll get back. Is that fine? Okay. Okay. Yes. Okay, let's get started. Yes, I can. Think of it as bilinearity is a simple idea. I'll tell you. I mean, don't get into what is represented there. Firstly, if I just tell you about this, uh, if you think about bilinearity is just saying that the inner products have to behave linearly with mixing. Think of it as the way it has been written down the slide as when you scale vectors, let's say if I double a vector, let's say there's a vector x. If I double this vector, right? If I multiply it with 2, the similarity also would double. If I perform similarity of this vector with any other vector, then in that case, the similarity would also double. So let's say, for example, if I am taking x, y, and if I take the double of the first vector, 2xy, in that case, the similarity would be nothing but equals to this. So this is one simple understanding that it is having. And the way it is written down there is you have, let's say, for example, if you scale a particular vector x with this the second vector with y with beta, and then you take a inner product with with y, it is almost similar to like taking the inner product between x and y and scaling the inner product plus taking the inner, let's say for example, this is z, not x. So let's say inner product between x and z and then scaling that, inner product between y and z and scaling that. Okay. So this is the first idea. And the second idea is built on the first idea itself. So basically, if you'll have to understand it, when you scale certain vectors, the inner product or the dot product also scales. That's the simplest possible meaning that you have to understand, right? The inner product or dot product also scales with the same unit by which you are scaling the vectors. That's the idea. That's essentially the idea. Okay. So there is nothing more important in bilinearity, and that is also not important from your exam point of view. Also from ML point of view, I have never, let's say in last 12, 13 years of my experience here, I have never seen someone or heard someone saying that we have to discuss about bilinear mapping and so on. These are just abstract concept brought in here so that inner product behave logically or they behave uh, linearly, I would say, right? So for the inner product to behave linearly with mixing, when I say mixing, you are basically scaling vectors, right? That's why it is important. But right now, I have only 14 more minutes, so I'll just give you an idea about two different things, and then I'll take the questions on the chat. Okay, so just let me finish up these two ideas about the angles and Cauchy inequality, because that is actually very important. Okay, so let me start with it. So let's say that we have just discussed about these two things, which is um, dot product x dot y, which is also written as x transpose y, and also when you take into account inner product, it can be written down as like this, right? So x comma y. So this is the generalized dot product. We call it as inner product, right? Generalized version of dot product. And you just looked into y. Now, one other important thing that I need to tell you is, if you think about, I told you that the matrix A is positive definiteness, let's say 10 0 0 1. If you have a matrix like this, it is giving more importance to the first vector. Now, why I have said that is, if you think about that, let's say for example, this is if I multiply this with a vector, okay, let's say for example, the matrix gets multiplied with the vector x1, x2. So the output would be 10x1 plus x2, right? Now, if I multiply this with the vector itself. So basically, this is the a into x, right? So this is a into x form. Now, if I multiply this a into x form with the second vector, which is x transpose, right? So let's say, for example, if I multiply it with x1 and x2, now what do I get? I get 10x1 square plus x2 square. So this entire thing, 10x1 plus x2 square, is nothing but x transpose ay. Sorry, x transpose ax, right? Now you see that x transpose ax is, there are two different things to look into. The first component is squared, second component is square, so it is never going to be a negative number, right? Because x1 would be some positive number, and x1 could be anything and some positive negative number, but that square is going to be positive. Second thing is, you the number here, which is 10, you gave more important to that dimension. So because you gave more important to that dimension, now what is happening? It is getting scaled by 10x1 square, right? So there were two dimensions to start with, x1 and x2, and the x1 dimension right now is more important than x2 because it is 10 times x1 square plus x2 square. So when you have these matrices like symmetric, positive, definite, these symmetric, positive, definite matrices are also important to give importance to certain features at certain times, and this is what you will build on that idea. But what I was telling you here is, when you go from dot products to more generalized notion of dot products, which are called as inner products, there is one other way of looking at dot products, which is like x dot y is equals to nothing but the length of x and length of y into cos of the angle between them. So think of it as, when you have two different vectors, let's say this is first vector, this is second vector, this is the angle between them, right? This is x and this is y. When you take dot product between them, it is almost not almost, it is actually same as taking the length of the first vector, taking the length of the second vector, and multiplying it with the cos of angle between them. Or you can also rewrite it as x dot y divided by the length of x, length of y is equals to cos theta, right? Now, this is what we call as cosine similarity. If you have to find out how similar, dissimilar to both vectors are, just take a dot product between them, divide it by their length. Basically, when you divide by their length, you are basically normalizing them, right? Now, what would happen because of this? You already know that cos theta has certain restrictions. Cos theta has its range from -1 to 1, right? It can be -1, 0, 1, or in between that range, -1 to 1, right? So if the dot product between them, let's say, for example, x dot y, if the numerator is 0, no matter whatever their length is, whatever their lengths are, if the dot product is 0, if the numerator is 0, meaning that the the cos theta would be basically 0, right? And cos theta is 0 only when the angle between them is, cos theta is 0 when is cos theta 0? Where are you guys? Here. 90 degrees, right? So yeah, exactly. So you already know about this particular part. So basically, when the vectors are like this, right? So you have x vector and y vector. If they are orthogonal, okay. So basically, when the vectors are orthogonal, then in that case, the angle between them would be 90 degrees, and then cos 90 would be 0. Now, if the vectors are in opposite directions, what would happen? Let's say, for example, this is x vector, this is y vector, the angle between them is 180 degrees. If the vectors are in opposite direction, then the angle between them is 180, cos 180 would be negative. Hence, you will say that they are in opposite direction. They are not aligned in the same direction. Their cosine similarity would be negative, -1, right? If they are aligned in the same direction, okay, or let's say in the same direction itself. The angle between them would be 0, cos 0 is 1, hence they are, the cosine similarity is maximum. If you have two different texts, this is where the text similarity also comes in. If you have two different texts, let's say text number one, someone's tweet number one, someone else's tweet. If you would want to find out similarity between them, just take a cosine similarity between them. If when you take cosine similarity and you found that the value comes out to be 0.8, it means that the angle between them is very small because the value is closer to 1, right? If the value is cosine similarity is 1, it means that both the tweets are exactly same, okay? Or they are actually similar somewhat, right? So they are in the same direction. So cosine similarity tells you the angle and the similarity between vectors in terms of angles, okay? And that is derived based on the same dot product idea. This is called as x dot y. And in the start of the lecture, I told you one thing. When you are looking from your eyes, what you do is you keep rotating your screen so that it gets aligned to a particular angle. The reason for that is the angle between your eyes and screen has to be zero to maximize the light intensity. This is the dot product that we have been seeing all our lives, but we might not have recognized it, right? It's simple idea. We are seeing it every single day. The maximum, the reason that we bend our head to see a particular thing is also because of the same thing, right? So all of these things are really important, but there is one particular thought which has been given in your slide, and that is called as Cauchy inequality, which says that x transpose y, it doesn't has any significance. They have, I don't know why the proof of that has been given. If you would want, I would share you the proof. That's not important, but that is actually not important. The intuition is important. The kind of problems coming from that particular slide is important, but that entire proof is not going to come in the exam. So I'll not go into that proof. Even I can do that, and I can share that proof with you. But the Cauchy inequality theorem, what it says is the dot product between two vectors, or let's say, for example, the cosine similarity between two vectors. This is the cosine similarity form. If you think about cos theta is equals to x transpose y by length of x, length of y. This is what we just did here, right? And this is equals to cos theta. And we already know that cos theta is equals to the range of that is in between -1 to 1. So you already know that it would be greater than -1 and less than 1. So this is what that Cauchy inequality is, which is mentioned in your slide. Okay. And this just says that the cosine similarity would revolve between -1 and 1. Now, if you have to prove orthogonality, let's say, for example, if you have to prove if two vectors are orthogonal, you just have to find this out, x transpose y and x dot y. And you will have to say that if x transpose y or x dot y is equals to 0, it means that the vectors are orthogonal. When I say orthogonal, what I mean is both the vectors are perpendicular to each other, this type of scenario. So the angle between them is 90 degree. And the vectors can only be orthogonal when the angle between them is 90 degree. And that's why you see x dot y or x transpose y being 0. Okay. So this if you have to think about it, think of these two. The best possible intuition that you can get to is, let's say there is first vector which is x is equals to 1 0, and the second vector y vector is equals to 0 1. And if you have to plot the first vector out, this is 1 0, and plot the second vector out, this is 0 1, right? Just take a dot product between them. 1 into 0 is 0, right? The dot product would be 1 dot 0 plus 0 dot 1. It is 0, right? The dot product is 0. And that's what I said. When you have two vectors which are perpendicular to each other, they are orthogonal, the dot product would always be 0, right? So this the idea that I in this lecture I wanted to give to all of you. I hope it was slightly and I will not be able to take up all of those questions. The reason for that is in front of your screens I haven't taken my breakfast, and I have a class starting in next 10 minutes. So I'll come back to your question maybe in the next class. But I'll not be able to take any questions right now because I have just a class in next 30 minutes from now. Okay. So I feel that you, if you go have questions, you can write to me, or in the chat, you can write to me. I know that there are 3 more minutes. I can possibly take one question, at most 1 or 2 questions, not more than that. So you decide which one has to be taken, right? No questions. Okay. Thanks everyone then. And let's take all of these questions in the next class. Okay. Thank you for joining. Thanks.
Thank you,
Sir.
sir.
Thank you.
Thank you.
Thank you.
Sir. Bye bye,
Thank you,
everyone.
sir.
Thank you. Thank you all.